The next reaction that you're going to perform this semester is the opposite of the dehydration that you have recently performed, and that is going to be the hydration of an alkene. The alkene in our experiment is going to be norbornene. Hopefully you have learned in lecture that when you hydrate an alkene, you get an alcohol product. And specifically here, we are doing an acid catalyzed hydration. So the first step of the mechanism is going to be to protonate the alkene. And this is going to take place in a Markovnikov fashion. So the proton will go to the less substituted side of the alkene and leave the positive charge in the more stable, more highly substituted position. This cation is then attacked by water to initially yield a protonated alcohol. And then finally, there's a proton transfer between the solvent water and the protonated alcohol to leave the neutral alcohol and hydronium ion. Looking at our specific alkene substrate, the acid we're going to use is sulfuric acid. So here's the proton transfer that takes place first to yield the norbornyl cation. And then this can be attacked in two different ways by the water, either via what we call an exo attack, as shown here, or an endo attack, as shown in the teal color. And note that depending on which way the water comes in to attack the cation, two different products could result. And so the nice thing is that their melting points are drastically different. So you're going to use the melting point as a way of figuring out which one of these stereoisomers that your reaction generates. As it turns out, the alcohol product of this reaction, so norborneol, readily sublimes at standard conditions and room temperature. And just a note here about the squiggly line notation that you see being used. This is a way of indicating that I'm not specifying stereochemistry. I'm just showing you that there's a hydroxyl group there, and it could be either the endo or the exo isomer based on this drawing. Hopefully you remember that sublimation is the transition directly from a solid to a gas without ever entering the liquid phase. And not a lot of solids will readily sublime at standard pressure and at room temperature. This norborneol will. In order for this to happen, the solid needs to have significant vapor pressure at room temperature. And so, for example, solids that have a strong smell associated with them will be subliming, because that's why we can smell the vapors coming off of the solid. A solid that doesn't have a smell associated with it, but that you guys are probably all familiar with, is dry ice. And if you've ever seen a block of dry ice sit out over time, it never will melt, but it will go away as it enters the gas phase. And so that's an example of sublimation. Of course, the opposite of sublimation is deposition, and that is going back from the gas to the solid phase. And we're going to use this idea of sublimation and deposition to purify our product. And the strategy is something like this, where you have the solid product, you sublime it into the gas phase, and then you redeposit that as a solid. And to see how this works a little bit more in detail, you should watch the part of the soft chalk module, the separations module, on sublimation. As a brief aside here, this is a little bit of an advanced topic, but I just want to talk to you a little bit about the norbornyl cation itself. And the two structures I'm showing you here, there was a lot of controversy for a long time about whether or not this cation existed in equilibrium between these three different structures. So actually three unique structures that were existing in equilibrium versus being a resonance hybrid of these three structures. And as it turned out, after much research and much debate, this is an example of what we call a non-classical carbocation, and it is indeed a resonance hybrid of the three structures. The drawing at the bottom, believe it or not, is the same as the drawing at the top, but just from a different perspective. And the dashed lines are the way of showing where the positive charge is delocalized. I'm not showing you this because I expect you to include this in your lab report in your discussion. This is, again, a rather advanced topic. You can read about it if you want. There's been a lot of research done, even some Nobel Prize work done with this cation. But I'm showing you this because it might help you to visualize why the water attacks from the angle that it does and gives the stereochemical outcome that it does. So when you're thinking about this and you get your melting point data, you can go back and look at this picture and see if it helps or not. Again, it's not required that you talk about this in your lab report.